Good morning, good afternoon, and good evening, ladies and gentlemen. My name is Nadir Husein from GeoSplit company. I have pleasure today to present to you the use of nanomaterial quantum dot traces in the domain of data-driven models, what we call the digital platform as a tool for efficient reservoir management. So this is the agenda of today's presentation. I will start it off by explaining the process of using quantum dot based nanomaterials in the inflow traces domain. Then I will briefly discuss the applications in a single well as well as in multi-well applications. And then I will spend most of the time discussing the use of data or dynamic data obtained from production surveillance using traces in data-driven models where we use machine learning to be able to do a predictive analysis and better decision making in reservoir management and ultimately hydrocarbon recovery. I will close the presentation by showing you the current dashboard that is being developed to use all those data-driven tools. So I will start off with explaining the workflow of using quantum dot traces in production surveillance. So this technology uses quantum dots, which are nanocrystals, uh, basically 2 to 10 nanometers in size. And the key feature of those nanomaterials is the fact that when they are exposed to a certain electromagnetic excitation, or for example laser light, they emit a very distinct spectrum of electromagnetic waves. And what we can see with our naked eye is that they emit a very distinct colors. So the different combinations of quantum dots or those nanomaterials allows us to have unique signatures that we place downhole in the wellbore or in the reservoir, and later on captured on surface to be able to analyze the production profile. Today there are 63 different unique signatures that are used for tracing all three fluid phases, i.e. oil, water, and gas. So the nanomaterials, the quantum dots, are then placed in microspheres, which are typically from 200 nanometers to 1 micron in size. And actually, those microspheres are the particles that are controllably released in the fluid, captured on surface and analyzed in lab. As I mentioned, today we have composite materials where we place the microspheres containing the traces, and that material can be either hydrophilic or water wet, oleophilic or oil wet, and gas reactant. So all three fluid phases are being monitored with this technology. I'll draw your attention now in the middle part. So basically, this is how the various deployment methods that we have deploying the traces. The most common one is a coated propellant, where each unique signature is placed in every single fracturing stage at the tail of the stage. So once the well is put on production, the fluid passes over the coated propellant, releases the traces controllably in a controlled manner, and then the traces travel on surface where they are captured and analyzed in the lab. Another method is placing traces in downhole completions, typically in open hole completions which has swellable plackers, like multi-stage frac, ICD, ICV, or sand screen type completions, where the traces are put in very elastic material, wrapped around typically on a blank pipe, and then protected by shrouds. And again, once the reservoir fluid is passing through the downhole completion. It releases the traces. The traces travel on the surface and where they are captured and analyzed. The sampling on surface for liquid phases, meaning oil and water, is a quite simple process and requires taking samples on a wellhead, where the gas sampling is a bit more complex, where there is a need for a bypass line, and there are specially made mesh size filters to be able to capture the gas traces. The technology that's used to analyze the traces in this fluid sample is called flow cytometry, adopted from biotech. And the advantage of this technology is the fact that there is no need to shut in the well during the sampling period, and it still gives ability to do the quantitative analysis of zonal contribution and phase contribution to the total production rate. So this slide shows the operating principles of the polymer matrix, or what we use as a composite material to controllably release the traces. So basically, each composite material has the microspheres that contains the traces or unique signatures. It has the insoluble polymer net, so this green network, or if you see on electronic microscope image, this is this network, and the primary function of this network is to preserve mechanical properties of the material throughout the life of the well or the material that's placed downhole. There is also the peach type color, we call it functional filler, and this is a composite material that is designed based on which fluid phase we would like to trace. So we have a specialty materials for oil, materials for water, and materials for gas. So what happens is when fluid touches the composite material on a contact surface, the material swells. It creates we call it diffusion channels, where the microspheres containing traces line up one by one, and then those spheres are controllably released in the fluid flow only when there's enough kinetic energy or flow velocity on the contact surface area of the materials. Very important point is that there is a direct linear relationship between the number of the traces released in the fluid flow with the flow velocity, i.e. with the production rate. And because of that, we are able to do a very accurate quantitative analysis for the zonal production or zonal contribution to the total production. As I mentioned, I'm not going to go into details of it, but we use a flow cytometry technique adopted from biotech in conjunction with machine learning software, just because we want to ensure that efficiency and accuracy of the analysis guarantees the accuracy of results. So this slide shows the application in a single well. The key advantage of using inflow traces over conventional methods is the fact that it is interventionless, so you don't need any typical cold tubing conveyed production logging tools to obtain production profiling. So it substantially decreases operational and HSE risks, as well as substantially reduces the cost, and obviously enables the end users to use or to obtain production data coming from each zone in a more frequent manner. And then on top of that, one thing to mention is that typically those inflow traces have a longevity of production surveillance 5 years and above. So just to quickly give you a flavor of what you can get in terms of simple data is basically production contribution in this case of the two-phase flow, where you can see a production contribution of oil phase in every single zone. In this case, there are 5 zones in a horizontal section that has open hole downhole completion. And you can also see that you can obtain the zonal contribution of water of each zone. So this data gives another level of measurements of production when it comes to reservoir management, also when it comes to, for example, optimizing hydraulic fracturing designs, frac spacing, the length of horizontal sections during drilling, the well spacing, etc. It also can give a qualitative diagnostics to understand the work or performance of downhole control devices such as sliding sleeves, ICVs, ICDs, because using the traces in single isolated compartment can quickly give the idea if the ICV or sliding sleeves is in open or closed position, where is the water breakthrough coming or gas breakthrough coming from, etc. Obviously, getting a more dynamic data or a big data allows the end user now to identify the patterns and definitely make better decisions in optimizing the field development, production increase, and ultimately hydrocarbon recovery. With the involvement of using the inflow traces, there is more and more need to use this technology in a multi-well environment. Typically, when you have enhanced oil recovery techniques like water flooding, then the data obtained from zonal production profiling can be very useful to optimize water floods, understand or optimize the hydrocarbon recovery on individual well level, and be able to accurately update the reservoir hydrodynamic models to understand the water flooding efficiency. Again, just to remind, the beauty of this technology is the fact that you don't have to shut in the wells to get the results. You don't need to do an asset-heavy interventions in the wellbore to obtain the data. It's just literally taking samples on the wellhead and analyzing them in the lab. And because of that, this is enabler to do a more frequent or dynamic production profiling, which obviously aids into automating the predictive analysis and decision making when it comes to completion strategies, infill drilling, when it comes to specifically for hydraulic fracturing, how to optimize production per each individual frac. So the previous slides discussed how the inflow tracers technology can enable the users to obtain a large amount of data points when it comes to a zonal production contribution. And obviously this can enable now the use of different data-driven or machine learning models to be able to aid in a better decision-making. This slide shows a typical capacitance resistance model, which is a data-driven model specifically used in water flooding to understand the water flow from injector wells to obviously now each zone of horizontal producers where they are either hydraulically fractured or there is a downhole completion that has a physical barriers between different compartments. So if you look at this picture, now the inflow traces give a very detailed and accurate production profiling data for each of those zones. So there are 4 those here. And then, with the other parameters like water injection on those individual wells or injectors, now we can start analyzing the water flows from each injector to each of the compartment in horizontal sections. What can we do with this data? Obviously, we can evaluate the water flooding efficiency. We can, with the history matching, we can forecast fluid and oil production, and based on that, we can start optimizing the operation of those injectors. Like we can see with this now developed model, the effect of changing the injection rates of, for example, in this case, one or more of those injector wells, and then the impact of such changes to the production of this horizontal producers. Obviously, this can be the modeling and predictive analytics can be used as a plugin or a new input to existing reservoir simulators. So to follow on different use of this big data coming from zonal production contribution into machine learning model. So this slide shows a typical flow and water cut coefficients obtained between different injectors and then different horizontal producers. And obviously this can again give us a more accurate picture or hydrodynamic models to understand the efficiency of water flooding. Ideally, I put those two pictures just to understand that what we are trying to achieve in any water flooding project is to have a piston flow, meaning that you get 100% efficiency of the water injected, that it's going to push and produce the same amount or volume of hydrocarbons. But reality always shows us a water breakthrough, or when you have a more conductive let's say natural fractures, then the water does not it follows the path of least resistance, and that injection water is lost. So in this specific case, I just wanted to show interaction between two injectors and two producers, and from the table what we can deduce from the different coefficients for water cut, that this injector highlighted in green does affect the hydrocarbon production of both producers, and then this injector affects hydrocarbon production of this producer only. However, when we look at water injection profile through the coefficients obtained, we realize that the more water flow goes through this path, allowing a better hydrocarbon production in comparison to this streamline or path, which immediately can give us an insight to maybe alter the injection and ensure that the water cut here is reduced and hydrocarbon recovery is optimized. With the ability of obtaining a large amount of data from zonal production profiling, and when it's incorporated with other data of different wells or well clusters, it paves the way to make a unified digital platform where you use different digital architecture with eventually making automation of predictive analytics. I'm not going to go into details of each part of the system, but ultimately, gathering the data in one place, analyzing it in using different models, whether it's a data-driven model or physical models, can create algorithms to automate the predictive analytics or optimized decision making when it comes to field development, reservoir management, and ultimately hydrocarbon recovery. So once the right digital architecture is established, then the next step would be to use business analytics and business intelligence, and may basically create an interactive and user friendly dashboards, so the end user can easily visualize the optimization process, or the uh, predictive data in graphical modes, or maps, etc. And this would be the final step of using a digital platform for continuous automation and better reservoir management. So, in conclusion, we've seen in the presentation that the domain of inflow traces definitely is giving a next step change in production surveillance, where you don't need any intervention, substantially reducing operational HSE risks, and definitely enabling now to obtain a more frequent data that can be used in physical and data driven models or machine learning to improve or automate optimization of reservoir management. And with the right digital platform, with the right business analytics, business intelligence, and dashboards, then you have a complete package that allows the end user to better optimize reservoir management, increasing accuracy and efficiency. With this, I conclude my presentation and open the floor for any questions.